Welcome to Calculus, First Semester Calculus, Math 3A. I'm Carla Westfall. I'm your teacher. My pronouns are she, her, hers. I'm pretty informal, so I'm happy to answer to Carla. I've answered to that name all my life. I'm kind of used to it. If you're more comfortable, I do answer to Professor Westfall as well. I'm sorry that we can't be having this class in person. I really enjoy interacting with students and having you folks work together. I think it's more fun to learn when you can do that in a community. And I hope you will try to find ways to form virtual communities and to work with people in the class and have study partners even if you're doing that remotely. Okay. I should also specify that while I regret that we can't be having this class in person, that is in no way a criticism of the decision to move most classes online for this semester. I am really grateful to the administration for prioritizing the health and safety of the faculty, staff, and students. I think they made the right decision. I regret the fact that it was necessary, but I absolutely am grateful that that's the decision that was made, and I support that decision. Okay, so let's see. The orientation module is something that I hope you have already worked through. If not, you want to make sure that you do that today. Okay? The orientation module is really important because that establishes the ground rules for the class. It lets you know how you're going to be evaluated, how you're going to submit work for credit, how you're going to get feedback from me, and all of that sort of stuff. It's kind of important. And it is also boring. And you probably have an orientation to do in each and every one of your classes, and probably some of that information is redundant and you're really sick of it, but it is important. Because unlike with a live class, you're not going to have me every day coming in and making announcements and giving you reminders about things. Now, I will be communicating with you. I'll be communicating with you through email and through the announcements that I can make on Canvas. Those announcements should be automatically forwarding to your school email account. Now, I realize it's only old people like me who use email, but you have to pretend to be old and check your email this semester. Okay? If you don't like checking your school account, forward it to an account that you do check, but that's my primary way of communicating with you. Okay? And it's also the primary way that the school has of communicating with you. Okay. I'm old-fashioned. I use a landline. I can't send text messages. I can email. And I can email the class as a whole, or I can email people individually. Make sure that you are checking that, because if there are any announcements like the date of the exam has changed, not that I anticipate that, but if that does happen for some reason, if there's some new disaster that forces us to reschedule things, that's how I would let you know. So do make sure that you're checking that. Okay. I'm not going to spend a whole lot of time on ground rules and orientation stuff because that's in the orientation module, and during my office hours the first day of class I'll be working through that with people in person. Some of you may have done that with me already. Okay. What I want to do is start doing the math. Okay. So the first section that we do is section 2.1. We're starting in chapter 2. Now, chapter 1 is sort of a review chapter. I would strongly suggest that you take a look at the subjects that are covered in chapter 1 and see if there are any that you feel shaky on, and if so, maybe spend a little bit of time reviewing those. I'll also point out that there are appendices at the end of the book that also go over some review material. In particular, there's an appendix on trig. If you are shaky on your trig, do something about that now. You will be expected to be able to do trig and to be able to do it without a calculator. Okay. So, I expect you to be able to evaluate the trig functions at any quadrantal angle. That would mean any multiple of pi over 2. We'll always be working in radians. Okay. And any angle whose reference angle is nice. Any angle whose reference angle is pi over 6, which is 30 degrees, pi over 4, which is 45, or pi over 3, which would be 60 degrees. Okay. So make sure that you've got those skills. There are some additional resources available on our Canvas page, some additional resources for trig, so you can take a look at those. You can also use the appendix in your book if you feel like you need to brush up on that. That's also something that I'm happy to help you with. Okay, I love trig. So if you say, hey, can we play trig? I'll be very happy to play along. Okay, so office hours would be a great time to go over that if you feel shaky on that at all. Okay. All All right, but we are starting in chapter 2, 2.1, looking at some things called the tangent and velocity problems. Now, I've just been talking about trig, so you might see, oh my goodness, the very first section we're dealing with tangent, it's here already. That's not tangent in the sense of the tangent function in trigonometry. It does have a connection to that, but for our purposes, I think it's best to actually just think of that as, hey, we happen to be using the same word, but in a slightly different context. Okay, so we're going to be talking about these things called tangent lines. Okay. Now, if I just have a line, lines have slopes. The only exception to that, of course, would be a vertical line. For a vertical line, the slope is undefined. Vertical line is actually also the only type of line that is not a function. Ironically, vertical lines fail the vertical line test. Okay, so any line that is a function is going to have a slope. And the slope tells me some things about the behavior of the line. If I have a line like so, okay, I would say that that line is going up, okay? We always read things from left to right in math. Moving from left to right, we're moving up. Now, I'm a cyclist. As a cyclist, I don't look at hills as being one way. I could ride up this hill, and that might hurt, but then I could turn around at the top and I could ride down it, and that would be very fun. But mathematically, it's always going up because we always read our math left to right. Okay. And of course, if we call the slope m, if m is greater than 0, the line is going up. And if m is less than 0, the line is going down. Okay, so this would have a positive slope because it is going up. Now, here's another line. That would also have positive slope because it's also going up. And that line would have a slope that would be bigger than this one. I do want to be careful though. So the slope of a line is going to tell me whether the line is going up or down. I get that by just looking at the sign, plus or minus sign of it. Okay. It's also going to tell me something about steepness, but I don't want to say the steeper the line, the bigger the slope, because that's actually false. If I take a look here, that's a line that's fairly steep and going down. Here's a line that's much less steep, but also going down. This line does not have a bigger slope. This would maybe have a slope of, negative 2/3. This is maybe more like negative 2. Negative 2 is actually less than negative 2/3. So the rule with steepness is that if the absolute value of m1 is bigger than the absolute value of m2, here I'm just using m1 and m2 to represent two slopes, what that means is that line m1, the first line, that has m1 as its slope is steeper than the second. Okay, so the slope of a line gives me some information about these two things. What is the line doing? Is it going up or down? And how steep is it? Now, if I don't have a line, if I just have a curve, so let's say this is the graph of a function f of x. Now here, it doesn't really make sense for me to say, is that going up or down? Because, well, yes, it's doing both. First we go up, then we go down, then we go up, and then we go back down. And it also doesn't make sense for me to say, how steep is it? Because the steepness is constantly changing. So the questions that slope answers for us, up or down, and how steep, those questions don't make sense when I ask them about the entire graph of a curve. However, if I were to say, let's look at this point right here, I'm just going to say that's the point where the x value is x naught, so that the y value would be x naught f of x naught. If I say I'm talking about what happens here, are we going up or down as we pass through that point? Now I can answer that question. I can say, as we pass through that point, we were going up. Okay? And I can talk about how steep we were. Okay? So, if I estimate, it looks like we've got about the same steepness as that line that I just drew in. So the steepness of the curve at that point matches the steepness of this line. That line is what we call the tangent line. So the tangent line to f of x at a point on that curve is the line that best approximates the function. Now that's a fairly informal definition, because what do we mean by best approximates? But lines basically just do one thing. They either go up or down, or you could have a horizontal line that does neither, and always at the same rate. The slope doesn't change. So what the line is doing at this point should match what the curve is doing at that point. What the curve does changes. How steep the curve is changes. But at this particular point, I can say, at this particular point, it's behaving like this line. The tangent line is the line that captures the behavior of the curve at this point of tangency. And we're going to be concerned with trying to figure out how do I calculate that, and how do I get the slope of that tangent line. And that's actually going to be a new vocabulary word for us. The derivative of f at x naught. And if I specify a point x naught, an x value in the domain, notice that uniquely identifies a point on the curve. Because if I plug in x naught, I then get the corresponding y value, f of x naught. So just giving you the x value is enough to specify what point on the curve I'm talking about. The derivative of f at x naught is the slope of the tangent line. At x naught. And I'm just going to add a caveat, if it exists. It's entirely possible that it might not exist. There might not be a line that best approximates the function. But if there is, the slope of that is called the derivative. Okay? And that's going to be one of the big topics that we talk about this semester. So basically, lines have slope. That's a number that tells you what the line is doing. It describes the behavior of the line. Curves don't have a slope. They don't have a unique number that describes things. But the derivative is kind of the quote-unquote slope of the curve at a particular point. It's just that it varies. And so rather than calling it actually the slope of the curve at a point, we introduce this new vocabulary word, and we'll call it the derivative at a point. All right, so that's what we're going to be trying to find, and in the next video we'll take a look at an example and try to find one.